Hello. In today's lecture, I'll give you a generic method for constructing iterated hash functions. I'll prove that these iterated hash functions are collision resistant. However, the proof will make a very strong hypothesis. I'll then give you a brief history of iterated hash functions, including MD4, MD5, SHA, SHA-1, and SHA-256. I'll begin by describing Merkle's method for constructing iterated hash functions. An iterated hash function has two components: a fixed initializing value IV, which is a bit string of length n, and a compression function f, which maps bit strings of length n plus r to bit strings of length n. F should be efficiently computable. To compute the hash of a binary message of length b, which is less than 2 to the r, one does the following. First, break up x into r-bit blocks x1, x2, up to xt, where the last block xt is padded with 0 bits if necessary. Define the length block xt plus 1 to hold the right-justified binary representation of b. So b is stored in the right portion of the block, and the block is padded on its left with 0 bits to get a block of length r bits. Next, we'll define h0 to be the IV, and we'll recursively compute hi by applying the compression function to the concatenation of hi minus 1 and the message block xi. Note that each hi has bit length n, and each xi has bit length r. The input to f has bit length n plus r, whereas its output is n bits long. The HIs are called chaining variables. Finally, we'll define the hash of the message x to be the last block ht plus 1. Here is a diagram that depicts Merkle's hash function construction. The input to the compression function on the left is the n-bit IV and the r-bit first message block x1. F mixes up the bits of x1 and the bits of the IV and outputs h1. The chaining variable h1 and x2 are then input to f, which mixes up their bits and produces the chaining variable h2, and so on. The last block produced by f is the hash of x, so h is an n-bit hash function. One can expect that for a good compression function f, h of x is a very complicated mixture of the bits of the blocks of the message, the bits of the length block, and the bits of the IV. And so one can expect that h of x appears to be a random string of length n bits and bears no resemblance to the message x. Merkle's hash function construction comes with a very nice security guarantee. We have the following theorem. If the compression function f is collision resistant, then the hash function h is also collision resistant. The conclusion to Merkle's theorem is very appealing. It asserts that no one will ever find a fast method for finding collisions for h. However, the theorem also has a very strong hypothesis, namely that the compression function f is collision resistant. At first glance, the hypothesis might look very much like the conclusion, and so the theorem appears to be somewhat vacuous. However, the hypothesis is about collision resistance when the inputs have a fixed bit length, namely n plus r bits, whereas the conclusion is about collision resistance when the inputs can have any bit length less than 2 to the r. And so Merkle's theorem reduces the problem of designing collision-resistant hash functions to that of designing collision-resistant compression functions. Merkle's theorem is not an unconditional guarantee of collision resistance, but a conditional guarantee. As I mentioned, Merkle's theorem has a very nice security guarantee, namely that h is collision resistant. However, Merkle's theorem also has a strong hypothesis, namely that f is collision resistant. A major theme of cryptographic research is to formulate precise security definitions and assumptions, and then prove that a cryptographic protocol is secure under the stated assumptions. A security proof is certainly desirable since it rules out the possibility of attacks being discovered in the future. However, as we've seen with Merkle's theorem, it isn't always easy to assess the practical value that a security proof provides. For example, the assumptions in the security theorem might be unrealistic, false, or even circular. The proof itself might have errors in it. The security definition and model might not account for certain kinds of attacks that are considered realistic in practice. The proof might be asymptotic in nature, and hence not relevant when you pick parameters of a fixed length for practical use. And finally, the proof might have a large so-called tightness gap. If you're interested in the interplay between theory and practice in cryptography, and specifically in the role that security proofs can play in practice, you can check out some of the articles I've written on my webpage, anotherlook.ca. This is optional reading, of course. Okay, let's prove Merkle's theorem. I'll prove the contrapositive statement. So I'll suppose that H is not collision resistant, and then argue that F is also not collision resistant. Since H is not collision resistant, we can efficiently find two distinct messages X and X primed with the same hash value. Let the blocks of X be X1, X2 up to Xt. Let B be the bit length of X, and let Xt plus 1 be the length block. Similarly, let the blocks of X primed be X1 primed, X2 primed, up to X primed, T primed. Let B primed be the bit length of X primed, and let X primed, T prime plus 1 be the length block. We can now efficiently hash the messages X and X primed. When we hash X, the chaining variables are H0, H1, H2, up to Ht plus 1. And when we hash X primed, the chaining variables are H0, H1 primed, H2 primed, up to H prime T primed, H primed T prime plus 1. Since H of X equals H of X primed, the last two chaining variables are equal to each other. And so Ht plus 1 equals H primed T prime plus 1. I'll divide the remainder of the proof into two cases. The first case is when X and X primed have different bit lengths. Hence, the length blocks for X and X primed are different from each other, because the length blocks are the binary representations of the corresponding bit lengths. Looking now at the last equations in the two lists from the previous slide, the outputs of the functions are equal as we noted earlier. On the other hand, the inputs to F are different because Xt plus 1 is not equal to X prime T prime plus 1. And so the binary strings Ht Xt plus 1 and H prime T primed X prime T prime plus 1 is a collision for F that we have efficiently found. And this shows that F is not collision resistant. Let's now consider the case when X and X primed have the same bit length. Hence, they must have the same number of blocks and also the same length block. Since T equals T primed, the number of equations in this first list, which is T plus 2, equals the number of equations in the second list, which is T prime plus 2. And so there is a one-to-one correspondence between the equations in these two lists. Also, I can delete the primes from the T's that you see in the second list. Here I've deleted the T primes from the equations in the second list, and also lined up the equations in this one-to-one correspondence. Let's first examine the last equations in these two lists. We've observed that the hash values are equal to each other, as are the length blocks. Thus, if ht is not equal to h prime t, then we have a collision for f that we have efficiently found. So let's assume now that ht equals h prime t. So the chaining variables in the second last equation are equal. If the inputs to f in the second last equation, shown in pink, are unequal, then they form a collision for f and we're done. So let's assume that these inputs to f are equal. Hence, ht minus 1 equals h primed t minus 1, and xt equals x prime t. Now we look at the third last equations in the two lists. If the inputs to f shown in light blue are unequal, then they form a collision for f and we're done. So let's assume that the inputs are the same. Hence, ht minus 2 equals h prime t minus 2, and xt minus 1 equals x prime t minus 1. Continuing in this way, we must come across an equation in these two lists. Let's say the third equation, where the outputs of f are equal, but the inputs to f are different. If this were not the case, then h2 equals h2 primed, h1 equals h1 primed, and x2 equals x2 primed, and x1 equals x1 primed. But then, all the blocks of x and x primed are equal to each other, which is impossible since x is not equal to x primed. And so there must be at least one pair of equations in this list where the inputs to f are different, but the outputs are the same. And these inputs are a collision for f that we can find efficiently. Here's a concise summary of the argument. Let I be the largest index between 0 and t, for which hi xi plus 1 is not equal to hi primed x primed I plus 1. Such an I must exist since x and x primed are different messages. Then, these two strings are distinct inputs to f, whereas the outputs of f, hi plus 1 and h primed I plus 1, are equal to each other. Hence, these two strings form a collision for f that we have efficiently found. This shows that f is not collision resistant. And so we've proven that if h is not CR, then f is also not CR. MDX is a family of iterated hash functions. MD stands for message digest. Within this family, we have MD4, which is a 128-bit hash function designed by Ron Rivest in 1990. Rivest is the R in RSA. The Van Oorschot-Wiener algorithm can find an MD4 collision in time 2 to the 64. This amount of work would have been considered infeasible in the 1990s, even though it's feasible today. MD4 was the first hash function that was used in practice. And so it came as a big surprise when in 2004, Professor Xiaoyun Wang, a mathematician working at Shandong University in China, discovered a method for finding MD4 collisions by hand. This showed that MD4 was completely insecure from the point of view of collision resistance. MD5 is a strengthened version of MD4, also a 128-bit hash function designed by Ron Rivest in 1991. In 2004, Professor Wang and a colleague discovered a method that could find MD5 collisions in 2 to the 39 operations. This amount of work was considered feasible even in 2004. MD5 collisions can now be found in 2 to the 24 operations, which takes just a few seconds to execute on a laptop computer. The fastest method known for finding MD5 preimages is just a bit faster than the generic attack. And so MD5 should not be used if collision resistance is needed. On the other hand, it's probably okay as a pre-image resistant hash function. MD5 is still used today. One reason for MD5's continued use is that it was widely deployed in the 1990s and the 2000s, and it's expensive and cumbersome to replace all these implementations. For example, in 2006, it was reported that MD5 was implemented more than 850 times in Microsoft Windows source code. In 2014, Microsoft issued a patch that restricted the use of certificates with MD5 in Windows. The reason for the patch was the discovery of the Flame malware. The Flame malware contained a forged Microsoft certificate for Windows code signing. This forged certificate used a new zero-day MD5 chosen prefix collision attack. This attack was a sophisticated variant of Professor Wang's attack, and so most likely was designed by professional cryptographers and not by amateur hackers. The forged Microsoft certificates allowed an adversary to sign the malware with the fake Microsoft keys. The targeted computers were somehow enticed to download the malware. The certificate was shown as being valid, so the computers installed the malware. This gave the adversary the ability to turn on the microphone on the infected computers, also to record video and to search for files. As I mentioned, the discovery of the Flame malware forced Microsoft to disallow the use of MD5 for code signing. The Secure Hash Algorithm, or SHA, was designed by NSA mathematicians and standardized by NIST in 1993. SHA is a 160-bit iterated hash function loosely based on MD4. In 1994, NSA slightly modified SHA to SHA-1. This change was made to fix an undisclosed security weakness. 11 years later, in 2005, Professor Wang and her colleagues found collisions for SHA in 2 to the 39 operations. This new attack was much faster than the VW attack, which would have taken 2 to the 80 steps. It's plausible, although we don't know for sure, that the NSA discovered Wang's attack earlier in 1994, and this is why they modified SHA to SHA-1 to circumvent the attack. Also in 2005, Professor Wang discovered a collision-finding algorithm for SHA-1 that takes 2 to the 63 operations. This amount of computation was considered very difficult in 2005. And so, it wasn't until 2017 when Wang's attack was actually used to find the first SHA-1 collision. No attacks for finding preimages or second preimages for SHA-1 are known that are faster than the generic attacks. In 2001, the NSA proposed the SHA-2 family of iterated hash functions. The hash functions in this family have 4 output lengths: 224 bits, 256 bits, 384 bits, and 512 bits. As of the year 2024, no weaknesses in any of these hash functions have been discovered.
The rationale for these 4 output lengths is that the security levels of these hash functions against the VW collision finding attack is the same as the security level of triple DES, AES-128, AES-192, and AES-256 against exhaustive key search attacks. For example, the VW attack can find a SHA-224 collision in 2 to the power 112 operations, whereas the meet-in-the-middle attack on triple DES also takes 2 to the power 112 operations to find a secret key. Similarly, the VW attack can find a SHA-512 collision in 2 to the power 256 steps, whereas exhaustive key search on AES-256 also takes 2 to the power 256 operations.
The SHA-2 hash functions have been standardized by NIST in FIPS 180-2. Here is a summary of the effect that Professor Wang's attacks had on the security of popular iterated hash functions. This checkered history of iterated hash functions highlights the impossibility in obtaining a 100% guarantee that a cryptographic primitive will remain secure for the foreseeable future. Even though the cryptographic primitive might have been carefully designed and analyzed by experts, and even proven secure under some assumptions, there always remains a possibility that someone will discover a new attack in the future that will render the cryptographic primitive insecure. I'll conclude this lecture with some brief remarks on SHA-3. The hash functions in the SHA-2 family are similar to SHA-1, which in turn is similar to MD4. And so, after Professor Wang found her attacks in 2004 and 2005 on MD4, MD5, and SHA-1, there were lingering concerns that the SHA-1 weaknesses could eventually extend to SHA-2. For this reason, NIST began a hash function competition for the next generation of hash functions. 64 candidate hash functions were submitted in October 2008 by researchers from around the world. And in 2012, after extensive analysis, Keechak was selected as the winner. Keechak uses the so-called sponge construction and not Merkle's iterated hash design. SHA-3 is now being used in practice, but is not yet as widely deployed as SHA-2.
The next video lecture will provide a detailed description of SHA-256, the most commonly used hash function. Take care, and I'll see you in V3e.